Happy Wednesday, Samson. Happy 420.
Just mine.
How's my day going? It's good. It's good. Well, actually, no, it's something that we had a ECS research day today, and so I gave a presentation there. Apparently, the dean had no idea what my research has been about, so she went to the research day today, and she told me this is the first time I ever found out what your research is about. I'm like, okay, that's great. I'm working here for 3.5 years now. Well, I mean, she's very busy. I'm also not the well, I'm not the most public with my research too. I don't usually like presenting it, but
What is your research?
I do simulations of blood flow. So very similar to our 442 class.
Oh, that's cool.
That's basically my research.
Same. You should have told me. I had another. You want to take one?
I'm saving up for the calories I'm gonna eat once I get home.
I kind of want to get cake on the way home. Right? So I was going to ask you something. You want to take the sandwich? Let's take the sandwich. But like you're on keto, right? So you're not supposed to have bread?
I'm not supposed to.
Why don't you just have like bread or something?
I'm not supposed to eat canes in general.
Oh,
I'm not keep.
I don't know. Oh,
It's all bread.
I don't know. I see. But it's something.
It is good. So I break it every once in a while. I shouldn't be breaking it.
A little bit. We more go over kind of the theory behind the simulations more than that. I mean, you can apply it to those kinds of applications, but we kind of just talk about that just kind of in general, not really specifically. Yeah. I'm not too big an expert on medical devices, but I am an expert on simulation technology. Yeah. Hey, what's up?
Someone left their glasses back there, so they'll be back really soon, sure.
Okay.
I'm gonna leave them up here like last time.
Okay, cool, thanks.
How's your back day?
Better today, actually.
Good.
Yesterday I was suffering. Yesterday it was really bad, but then I went home and I laid down, I put an ice pack under, and I felt something click in place. And so I think I have a slip disc or something back there. And so yeah, I just haven't really been giving it a good chance to heal. And so yeah, I need to lay down in the ice pack.
Pretty severe. Yeah. Are you sure it's something that bad?
I mean, it feels a lot better. Like it was noticeably better after I felt that click. So it felt like something like went back into place after that, and that kind of cleared a lot of the pain. So
Well, hopefully it stays that way.
hope so too.
No more wrestling 50-pound dogs.
Yeah, thankfully not. My wife's parents came home last night, and so yeah, we're not gonna go see them for a while.
Well, I'll be right back.
Okay.
plans for the weekend?
Yeah, nothing in particular. Just rest, I guess.
Yeah.
I should be resting. I shouldn't be really out and about too much. How are you?
Studying for your exam and another.
Sounds fun.
How dare you?
It was a very exciting life.
I'm studying for mom. You should know.
Yeah, I got yours and 401 15 minutes after.
Oh man.
So that's stacked. Yeah, it's my favorite.
Hey Ian, what's up?
Sorry, I think someone got locked it up announcement, so
Oh,
yeah. Sorry. You'll be here like until the next lecture?
yeah, I'm here till 8:30, but you can just get it back to me just next time we see each other. So,
Okay.
yeah, don't worry about it.
Okay.
Hey, how's it going?
Good, how are
Good.
Yeah, it took us like literally an hour ago for me to be on the list, so I finally have everybody on the my whole person. But there's so many people that are eligible to be free. I get it. It's $55, but you know, you say that for most places, other places charge like 100, 150. We charge the bare minimum to be part of our program. Because normally if you get more stuff, they'll provide. Yeah, but I mean, at the end of the day, you get what you get. Something in the graduation. The other thing is if I want to put $95, so that's $40 for the graduation year. But yeah, but it's more justifiable Exciting.
Okay, it's 5:30, so let's go and get started today. All right, good afternoon, everyone. How's everyone doing today? Hanging in there, hanging in there. End of week 13. So after this, we have three more weeks, and so the end of semester is upon us. And so it's a stressful time, but also exciting because after that is I know for a lot of you is graduation, you know, which is really exciting. I'll be there at graduation, and after that is summer, so that's going to be even more exciting. Okay, and so the plan for today is we're going to continue our set of lecture notes on higher order convection schemes, and so I'm hoping actually we can finish it today. We'll see. And then of course our midterm exam is going to be on Monday. Okay, so originally it was today, but you know we pushed it back to Monday. Okay, and so I think I mentioned on Monday, but there's one last homework, but I am going to hold off until after we do the midterm so that you have just one thing to worry about on your plate at a time. Okay. Oh, did everyone get the review video? So I think I sent that out yesterday. Right, so I think I sent an email with the link to that. So hopefully that's there to help you study. Okay, and so that's it for my announcements. And so are there any questions on anything before we get started? Okay, all right. So let's go ahead and pick up where we left off. All right. Okay, so last time, in the second half of the class, we introduced this idea of a higher order convection scheme. And so what that basically means is that, instead of using our regular central difference, we want to use a more accurate scheme to, improve the accuracy for convection, okay? Because what we've seen in the past, and this is true for both finite difference and finite volumes, that with our usual central difference scheme, we run into a lot of issues with the simulation, right? So we have issues with stability, that's number one. But we also have issues of cross-stream diffusion. And so what we're hoping is that by using a higher order scheme, we can fix a lot of these issues and not really have to worry. Okay? And so there's two parts of this lecture notes. And so the first part, of course, is the finite difference version. And then after that, we'll do the finite volume version. Okay? And so last time we introduced the finite difference one. And so what we say is that, instead of using our usual central difference, we can take our convection derivative and discretize it like the following. So we have just our normal d phi dx. And so we can say this is minus phi I plus 2 I plus 2 plus 8 phi I plus 1 minus 8 phi I minus 1 plus phi I minus 2 all divided by 12 delta x. Okay. All right, and so if we use this scheme right here, what we saw last time is that this scheme is fourth order accurate. Okay. That's a big improvement. And so, our usual central difference is only second order accurate. And if we use an upwinding scheme like a forward or backward difference, then we end up with only first order accuracy, right? So fourth order is just that much better. Right? And so this is great. And so this is going to fix a lot of our issues. The problem with this is that we're going to need to do some additional work. Okay. And so the tough part with using these higher order schemes is that they usually involve more and more neighbors. And so of course, having more neighbors, it's gonna take us a bit more work to generate the equations. But I think more importantly, it's gonna present some logistical challenges when we write the code, okay? And you'll see how that is in a second. Okay? Because in order to use this, this method here, or to use this scheme, what this requires is that we not only have neighbors on our left and right, but we also have to have our neighbors have neighbors as well, okay? And so in other words, we need neighbors that are two-way in both directions, both left and right, in order for this to work. Okay? And so this will work for a lot of the interior nodes. And so, if you have a very fine mesh, chances are you're not going to have too much trouble finding, extra neighbors on either side. But if you're close to the boundaries, or if you have a very coarse mesh, then it can be a little bit difficult. Okay. And so you're going to need to rely on if statements in your code in order to make this work. Okay, and so you'll see very soon in an example how this is. Okay, so that's just a recap from last time. So are there any questions on this before we jump into an example? Okay, all right, so let's do an example just so we can see how this goes. Okay. And we're going to jump right into a 2D case because in 1D it doesn't make that big of a difference. 1D you can just use central difference just fine. But in 2D, that's where you see these high order schemes really start to make a big difference. Okay, so we're going to jump right into a 2D example. And so this 2D example, we have 10 partial phi partial x plus 75 partial phi partial y is equal to 3 partial squared phi partial x squared plus partial squared phi partial y squared. Okay. And we want to solve this on the following grid, or following domain, I should say. And so we're going to have Dirichlet boundary conditions all around. So we have phi is equal to 25, phi is equal to 25. Here's equal phi, here phi is going to equal to 50. And up top, we have phi is equal to 50 as well. Okay. All right, and so we want to solve this equation for with finite differences. Okay. And in particular, for the convection terms, we want to use our fourth order scheme. All right, so we're going to follow the same process that we used to for finite differences, and so we're just going to take every single one of our derivatives and just plug in their finite difference representation. Okay? Then we're going to work through the algebra, rearrange some of the terms, so that we can get coefficients for each of the important p values. Okay, so that's the setup for the problem, and so we're gonna do some calculations by hand first, and then I'll show you how this is implemented in MATLAB. And remember, for your final project, you have to implement higher order schemes like this in order to get full credit. And so this is something that's good to know. Okay. Any questions on the setup for this problem? Okay, so let's go ahead and go start rolling. And so, just like we used to do, I'm going to take all our derivatives here and plug in their finite difference representation. And so first we have our x convection. And so we have 10. And then we have a minus bi plus 2, comma j, plus 8 bi plus 1, comma j, minus 8 phi I minus 1, comma j, plus phi I minus 2, comma j. Okay. We have to include the j. We have to include the j terms because we're in 2D. It's all divided by 12 delta x. Next, we have the y convection. And so the y convection is the 75 minus phi I j plus 2 plus 8 phi I j plus 1 minus 8 phi I j minus 1 plus phi I j minus 2. Okay. Right, so this is going to be 12 delta y. And then we have the diffusion terms. And so the diffusion is going to stay the same. And so we don't have to modify anything with the diffusion. Okay. And so let me go ahead and just kind of simplify this very quickly. And so for the diffusion, we have k divided by delta squared, right? And so, for the finite difference approximation for diffusion, we plug in a finite difference, we end up with delta squared on the bottom. And so I'm just going to pull that one out. Okay. And so if we work through the numbers here, we get phi I plus 1, comma j, plus phi I minus 1, comma j, plus phi I j plus 1, plus phi I j minus 1, okay, minus 4 phi I comma j. Okay. All right, and that's it. Okay, so for the diffusion term, we don't have any I plus 2s, I minus 2s, j plus 2, j minus 2, because we're only looking at the immediate neighbors for diffusion, right? Diffusion was never an issue. Diffusion was always kind of the good kid in the family, right? And so it's only the convection term that needs correction. Okay, and so the next step, of course, is we're going to simplify this because we want to put this in terms of coefficients, right? Because eventually we're going to implement this in MATLAB, and we want to extract what those coefficients are for those different terms. Okay? Okay, so this is a lot of kind of rearranging, a lot of kind of moving stuff around, and so I'm just going to go ahead and skip the answer. I will say though that I think compared to the equations that we did before, just to kind of make it a little bit more consistent with the form that we've been using later in the class, I'm going to take everything in this equation and multiply it by the grid spacing squared. Okay? And of course, that means we're going to assume that delta x and delta y are the same. And so if we do that, we end up with the following. And so we have a minus u delta divided by 12. That's the coefficient for phi I plus 2, comma j, plus 2 delta divided by 3 minus k, phi I plus 1, comma j, plus, or excuse me, minus 2u delta. Okay. Where u is 10, I guess I kind of plugged in inadvertently. But this one's better because this will be general, so you can just kind of plug this in as you go. Okay. All right, then we have a minus 2u delta divided by 3 minus k, and this is the coefficient for phi I minus 1, comma j. Then we have a positive u delta divided by 12, and this is the coefficient for phi I minus 2, comma j. Okay, so that's all the terms that are in the I direction. So now let's do the j direction. And so in j direction, we have minus V delta divided by 12, Bij plus 2, plus 2 delta V divided by 3, minus K, Bij plus 1, plus minus 2 delta V divided by 3, minus K, Bij minus 1, plus V delta divided by 12, Bij minus 2. Okay. And so, at first it doesn't seem like it's a big deal because, we're just adding, we're just adding two neighbors, but just adding two neighbors here is ending up being a lot of work, as you can see. Right? And this is a steady problem. And so this gets even worse once you have to implement this with implicit, explicit Euler. Okay. All right, and then finally we have the phi ij term. And so for that, it's just going to be a 4k phi I comma j. Okay. And so if you notice, compared to the previous equation, we moved the diffusion terms from the right to the left. And so all that's left on the right now is just going to be 0. And so this right here is our finite difference equation, which utilizes a higher order convection scheme. Okay. All right. Of course, the way that we define these, we defined this equation, we rearranged it. We designed it in such a way that these coefficients can be plopped basically right into MATLAB. Okay, and so this is just going to go directly into the A matrix on the left-hand side, which you'll see in just a second. Because in a second, we'll go over the MATLAB code, which shows you how to implement this bad boy. Okay. And so this is the best case scenario. And so this is basically a case when you have two neighbors on the left, two neighbors on the right, two neighbors above, two neighbors below. Okay. But what if you don't have enough neighbors? And so it can happen. And in fact, we've seen a situation like this before, right? So even when you're just using a basic central difference or kind of first order, second order schemes, it requires you to have at least one node that's bordering you on all directions, right? That was our cross pattern. But we saw, there were cases when we had our boundary conditions, right? And so if our node was sitting on a boundary, that means, of course, we didn't have enough neighbors because there's no neighbors past that boundary. And we have to resort to using the boundary condition equation. Okay? And so basically this can happen in two situations. So one, you are on a boundary. Okay? Or you're on one of the domain boundaries. And so in that case, if you're on a domain boundary, that means you can just simply use the boundary condition equation. So that's no different. And so that's basically what we've been doing with finite differences, right? And so if the node's on a boundary, we just use either the equation for the Dirichlet boundary condition or the Neumann boundary condition and just plug that right in there. Okay? But with these higher order schemes, you know, there's another scenario or another possibility for you to not have enough neighbors, but you don't necessarily have to be on a boundary. Okay, and so that can happen when you're next to a boundary, right? And so you're kind of just one node off from a boundary, and so that you don't have two neighbors in that direction. And these are tricky because, you know, you don't have enough neighbors to form the higher order scheme, but you're not on the boundary. And so you can't form a boundary condition equation from this, okay? And so in these, you have to kind of compromise. And so you have to say that, you know, I don't have enough neighbors for the higher order scheme. But what I can use is kind of the old school basic central difference scheme. You can use the old school central difference, or you can use the old school upwinding, okay, whichever one the problem calls for. And so if you draw this out, you know, we have our square domain. We can basically mark different regions of that domain where in terms of what scheme that we can use. And so here is our domain. And so first let me mark the boundary nodes, okay? And so everything that's within this kind of purple triangle or purple rectangle, excuse me. Okay. And so the purple square is going to engulf the boundary. And so anything within this purple boundary, these you would use boundary condition terms, okay? Right. If you go one layer on the inside, then you're going to be in the second case above, and so you're not going to have enough neighbor nodes to use the higher order scheme. But what you can do is you can use kind of the basic scheme. Okay, and so if I were to draw another ring, you know, it looks like this. And so in the green right here, we're going to use old or basic convection scheme. Okay. But then once you move beyond that and you get kind of one layer more on the interior, that's when you can start to use the higher order scheme, because everything on the totally interior here has enough neighbors to get it done. Okay. So everything in the yellow here is higher order scheme. Okay. Right. So the size of these regions, you know, I exaggerated, of course, because it's an image. But the size of these regions can depend on how coarse or how fine your grid is going to be. Okay, any questions on this? Okay, actually, you know, before we jump into MATLAB, let me go ahead and rewrite out the central scheme, because I'm going to use it maybe slightly different format than we've used before. Okay. All right, so what we can say for basic central difference, if we use just kind of a central difference scheme for all the convections, we get a form that looks like this. So we have U delta divided by 2 minus K, BI plus 1 comma J plus minus U delta divided by 2 minus k, vi minus 1 comma j, plus v delta divided by 2 minus k, vi j plus 1, plus minus v delta divided by 2 minus k, vi j minus 1, okay, plus 4k vi comma j is equal to 0. Okay. All right, so that's our basic scheme. And so you can see that we only have neighbors plus 1 or minus 1 from phi comma j, and the coefficients are of course different as well. Okay. Okay. Any questions before we take this to MATLAB to see how it's implemented? Okay. All right. So let's go ahead and move on to MATLAB. So let me go ahead and share my screen here. Okay, and so this code you can find on Canvas. And so if you go to our course website and you go to week 13, oops. Okay. Week 13, you go to higher order schemes. This is the second code that you see down there. And so it's the 2D advection diffusion finite difference with higher order. Okay, so let's look at this code. And so, this particular code has been modified to solve the problem that we brought in the class. Okay. Can I show the notes real quick? Yes. Let me share. Anyone else need this for a quick second? Okay. All right. So let me go back to MATLAB. Okay. All right. So here is our MATLAB code. Okay. So if you go to the course website, you go to week 13. This is the second code that's posted on the week 13 page. Right. Okay. And so the top section, there's not much to say here. This is the same as it usually is. And so we have the length of the domain. We have the number of grid points in each direction. Okay. And I think most importantly, we've defined the values for k, the x velocity, which is u, and the y velocity, which is v. Okay. All right, so let's come down into these equations. So it's been a while since we've looked at a finite difference code, but hopefully you remember what the format for that is. Okay. Okay, so first thing we do is we loop over all of the interior nodes. Okay, and so we do 4i is equal to 2 colon nx minus 1. And then 4j is equal to 2 colon ny minus 1. Okay. Notice how we offset these, and so we don't visit the boundary nodes because we're going to apply boundary conditions later on in the equation. Okay. Okay, and so from here you see some pretty standard fare, and so you can see here that we compute the ID numbers for my ID. Okay, so this is our classical 2D node ID equation, and so we do nx times j minus 1 plus I. And then we adjust this equation to get all of the adjacent neighbors. And so the left ID is going to be I minus 1. And so we replace I with I minus 1. Okay. The right ID, we replace I with I plus 1. Okay. Up ID, we replace J minus 1 with J. And with down ID, we replace J minus 1 with J minus 2. Okay. Okay. But we also need these. And so, because we'll be implementing a higher order scheme, we also need the ID numbers for all of the, what I call the distant neighbors, okay? Distant, not distance. Okay. All right, and so I've labeled these basically left ID 2, right ID 2, up ID, and down ID 2, okay? And so they're very similar to, the ones up here. It's just that I added 1 to either I or J, depending on, which direction that we're going. Okay. And so if you were to draw the stencil, let me go ahead and draw that really quick. Okay. And so for a typical node, actually we're in finite differences. Let me draw a node. Okay. Right. And so here is node I comma j. Okay. And so if we need both j plus 1 and j plus 2, it would look something like that. Okay. We have j minus 1, j minus 2. I plus 1, I plus 2, I minus 1, I minus 2. Okay. And so we still have this kind of cross-shaped pattern, but now it just extends a bit further. Okay. Notice how we don't use any of the diagonal neighbors. And so we don't use this one or this one. Okay. We just keep extending in the X and Y direction, right? And so we don't use any of the diagonal neighbors at all. Okay, and so let's go through the code now. And so first thing we do is we define the diffusion contributions. Okay, because no matter if we end up using a higher order scheme or a modal order scheme, you know, these are going to be the same. And so, you know, if you look at the diffusion derivatives in our original equation, you'll see that they kind of produce the following coefficients. And so we have a positive 4k for phi I comma j, and then a coefficient of minus k for all the immediate adjacent neighbors. So the left neighbor, the right neighbor, the top neighbor, and the down neighbor. Okay, so that's the easy part. And so, you know, that's we've been doing that for, you know, for months now. The more difficult part here is, of course, going to be the implementation of the higher order scheme. Okay. And so let's kind of first read this if statement and to try to understand, you know, what's the logic behind it, right? And so we're checking here, right? And so we're checking the I coordinate. And so we're checking to see if I is equal to 2, or if I is equal to nx minus 1, right? I think it's a little bit easier to see what's going on with I equal to 2, right? Because if we have our domain here, right? Okay. If I is equal to 2, right? And so we label this 1, 2, 3, 4, 5. Okay. And so if I is equal to 2, you know, we would be using this node right here, right? Because it's the second one in the list. Right? Let's check and see if we can apply the higher order scheme to this node. Okay. So remember, the requirements for the higher order scheme is that we have 2 neighbors in that direction, in all directions, right? And so let's count the neighbors. And so if we go to the right, okay, we have 1. We have 2 neighbors, right? So we have our immediate neighbor is 3, and our distant neighbor is 4. Okay. Now let's go to the left. And so on left we have 1 neighbor, and then we have a tragedy, right? And so someone fell off the number line. Okay, and so you can see on the left side we don't have enough neighbors, right? And so, you know, what this tells us that is if I is equal to 2, that means we don't have enough x neighbors to do the higher order scheme. And so what we're going to do is we're going to fall back on our usual central difference to discretize this, this part. Okay, and so the code here should look very similar. And so if you use a basic central difference, then on the left ID, we're going to subtract a minus u delta x divided by 2. And on the right ID, we're going to add a u delta x divided by 2. Okay, so that's a pretty basic central differencing. Okay. And so, but, you know, if we do have enough neighbors, we can go ahead and implement the higher order scheme, right? And so that's going to involve coefficients for left ID 2, right ID, and right ID 2. All right, so let's do the left ID first. And so left ID, if we go to your finite difference equation, okay, for left ID, which is I minus 1 comma j, you can see here that we have a coefficient of minus 2u delta x divided by 3. Okay. And so that term is validated. Okay. Next, for left ID 2, we have a positive u delta x divided by 12. Right. For the right ID, we have a positive 2u delta x divided by 3. And for the right ID 2, or the ID number 2 away, then we end up with a minus x velocity times dx divided by 12. Okay. Okay, and so of course, you know, the biggest difference here compared to our usual codes is that we have to check. And so we have to check to make sure that we have enough neighbors to implement or execute the high order scheme. And if you don't, you have to fall back on, you know, what you already know, which is basic central difference. Okay. Notice how we haven't taken care of the boundary conditions yet, but that'll come a bit later. But I wanted to kind of explain this this part here first. Okay. Any questions on any of that? Yeah.
So now that we take care of determining if there's an up or not neighbors.
And so if you write this if statement, it'll handle that for you.
Is there a way to do it by hand or would it take too long?
I mean, it's going to be different for every grid, right? And so if you make a finer grid, then the numbering is going to be very different from each other, right? And so you could definitely do it by hand. And so if you were to do this on like a very coarse grid, you could definitely write out the equations by hand. There's no problem with that. But for the code, we're just kind of setting it up so MATLAB can determine, which is best. Because if I change this, and so if I change this mesh to, let's say I change to 100 by 100, then we want the code to kind of adjust automatically to that. And so that's why we do it in terms of I, in this case, just I, and what position our I is. Okay, so that's the logic for the X direction. And so we're going to follow the same logic for the Y direction, right? And so you can see here the code looks very similar. And so we're going to check and see if we have enough neighbors. And so we check and see if J is equal to 2, or if J is equal to NY minus 1. And if it is, that means we don't have enough neighbors. Then we go through with our normal central differencing. Okay? But if we do have enough neighbors, then we use the higher order scheme. Okay? And so the coefficients for that are listed as follows. Okay. And so I think that's the only difference with the code. And so everything else is more or less the same. And so we have boundary conditions, but this is fairly straightforward because they're all Frischway. Okay. And we've seen this dozens of times before. So let me go ahead and run this code. Maybe I should have made 100 by 100. That's okay. It'll be a beautiful image. Oh, 11 seconds, not bad. Okay, and so here's our result. Right? And so in this case, I used 100 by 100, so it looks very, very smooth. But that's kind of overkill, right? And so I think I chose this example because it's one that we did previously when we first did convection with finite differences, right? And so if you compare this solution to the other one, I mean, first of all, you should see that they look very, very similar, right? If not exactly the same. But this shows you that the higher order scheme that we did, it's not, it's a real approximation, and you get a correct answer from it, just based on how similar this is with the other one. Okay, and so that's higher order schemes with finite differences. Any questions on this? Okay, all right. So let me go back to the iPad, and let's talk about how we can do higher order schemes with finite volumes. I don't know why it's doing this. Okay, higher order schemes with finite volumes. Okay, and so again, I'm going to go ahead and skip right to 2D. Just because you kind of see these benefits in 2D, but also your final projects are in 2D as well, and so that's I think that's going to be most useful for people. All right, and so we actually just finished going over this on Monday, and so when you do convection diffusion with finite volumes, remember the way that we end up doing it was we had to evaluate our 4 integrals. Okay? Right, and so that was kind of the basis of all the equations that we did, was evaluating those 4 integrals. And so in other words, we had something like this, where we had an integral of phi v n minus k gradient of phi dot n hat ds. Okay. And so let's say this is on the east integral, right? And so, or the east edge. And so we have equivalent integrals for the north, the south, and the west edges, okay? And so in our usual approximation, what we did was we said this is equal to phi sub e multiplied by u minus k partial phi partial x e, okay? Oh, excuse me. So this is an upwinding form, okay? Let me write that, upwinding. And because if it wasn't upwinding, then instead of phi sub e, we would take the or excuse me, I'm sorry, we haven't done anything yet. So this phi sub e is just the this is just the edge value. I'm sorry. Okay. All right. And so if we were to solve this equation with usual central difference, which is what we did on Monday, we would replace this with a simple average, right? Because what we would say is that phi little e is equal to phi sub c plus phi sub e divided by 2. Okay. And so that's how we implemented basic central difference using finite volumes. Okay. And since this is analogous to central difference and finite differences, we saw that this is second order accurate. Okay. Okay. And so just along with the theme of these lecture notes, we want to improve this method. And so we want to use a higher order scheme for this, instead of the central scheme. Okay. Okay. All right, so what does that look like? And so what does it look like for a high order representation for this, right? Well, let's kind of see what we did for finite differences, right? And so for this kind of simple averaging, we involve two neighboring values, right? So we involve phi sub e and phi sub c, okay? And so if we go by the logic of our finite differences, a higher order scheme is going to pull in more neighbors. So we're going to have to involve more cells, okay? And so we're going to have more that joins this party rather than those two. For a fourth order scheme, we invited two more people to the party, right? And so we invited our neighbors, okay? And so in finite volumes, we can do that too. But, in finite volumes, we have kind of another way to think about this, okay? And so let me go ahead and draw this picture for you. And so, normally what we have two neighboring cells, right? And so we have phi sub c and phi sub big E, right? And so those are the cell-centered values for our finite volume method, right? The value that we want to estimate is right in between, right? And so this is phi sub e, phi sub little e, and that's the value that comes straight out from the integral, okay? If you remember, when we first started talking about finite volumes, what we've kind of been implicitly assuming is that we have a linear variation between phi sub c and phi sub e in the neighboring cell, okay? And so schematically, you know, it would look like this. And so we had the values of phi sub c and phi sub e, right? They don't necessarily have to be like this. And so, you know, phi sub c might be bigger than phi sub e, but, you know, this is just the idea, right? And so by drawing this linear line or this linear approximation, you know, we were able to extract quite a few things, right? So first of all, you know, we could have the slope, okay? And so the slope, we use that as part of our diffusion term, okay? But we don't really care about the slope right now because we're talking about convection. Okay. All right, and so the other thing that we're able to do is so that, you know, if we're writing just along this a linear line, and we wanted to estimate the value of this line at this point, right? And so the value of phi at this point for a linear line is simply just going to be the average between the two. Okay. Okay. This is for a linear line. Okay. But, you know, linear lines are not the only types of lines out there. You know, there's lots of different lines, you know, and so you know, what if we try to use a different type of function or a different type of line to form this approximation? Okay. Okay. All right. And so, you know, there's really only one direction to go. And so a linear curve is kind of the simplest one that you can think of. And so you can't really make it simpler than that, but we can make it more complex. And so let's go up in complexity. And so instead of a linear line, let's do a quadratic line. Okay. Okay. So that seems logical, right? And so the next step up from linear is quadratic. And so let's do that. Okay. But we have a problem. Okay. For a generic quadratic function, right? And so a quadratic function that's most general is given by the following. And so we have a0 plus a1x plus a2x squared, right? And so it has to include all of these terms, okay, so we can't leave anyone out. The problem with this is that we have three unknown coefficients, right? Or three, you can think of them as 3 degrees of freedom. And so we have a0, a1, and a2. And so this is degree of freedom 1, 2, 3, okay? In order to solve for those three coefficients, you know, we're going to need to have 3 control points, right? This wasn't an issue in linear before, and so for a linear function, let me just draw you a linear function. Okay. And so a linear function is going to be let me use different terminology, and so a generic linear function will just be mx plus b, right? Where our degrees of freedom here are m, the slope, and b, the offset, or the y-intercept. Okay. All right. And so before, you know, we could solve for m and we can solve for b just using our 2 neighboring cells, right? Okay. And so there's a direct correlation between, you know, the complexity of the function and how many cells that you have to involve. Okay. And so it makes sense for a quadratic function, we're going to need to have 3 cells worth of information. Okay. Okay, so that makes perfect sense, right? And so three degrees of freedom, 3 cells. Okay. But we have an issue here, right? And so we need to add one more cell to this party right here. Okay. The question is, do we put a cell on the left? Okay. Okay. And so do we pull in the information from the left, or do we pull in the information from the right? Okay. We can go either way, right? And so actually, you both are actually valid. And so you can pull information from one or the other. Okay. But then how do you determine which way to go, right? So and unfortunately, it's not just a preference thing. It's not just a coin flip just to go one or the other. There are better ways to choose one or the other. Okay. And so this particular scheme, this quadratic one, is not only higher order, but it's also upwinding. Okay. And so not only is it going to be more accurate than our basic central difference, but it's going to have much stronger stability properties as well because it's upwinding. Okay. And by upwinding, what I mean by that is, we're going to pick a direction. And so the direction that we pick is going to be on whichever side is more upstream of the convection velocity. Okay. Okay. Right. So this will probably be the most complex scheme that we go over in this class, but I think it has all the nice properties, right? And in fact, we don't have time to go over CFD in this class, but if we did, you'll see that a lot of CFD codes utilize this scheme. Okay, it's utilized so much it has a cool name. Okay. It's actually called the quick scheme. Okay. Which sounds silly, right? And so everyone knows that acronyms are only just for really cringy politicians, but this is this acronym is actually really cool. Okay, so let's actually break this down. So it is an acronym, and it all makes sense. Okay, and so the Q here stands for quadratic. Okay, the U stands for upwinding. The I here stands for interpolation. Okay. The C stands for convective. And the K stands for kinematics. Okay. And so the quick scheme stands for quadratic upwinding interpolation for convective kinematics. Okay. It's a mouthful, so people just say quick. Okay. And I have to really applaud the person who developed this scheme, because what scientists tend to do is that they come up with something like this, they name it after themselves. But this person actually gave it a name that actually makes sense, and it's actually really cool as well, right? Unless this person's name was actually even Quick. I know some people have the last name Quick, and so if that's the case, then shame on this person. But if not, it's a really cool name that they came up with. Okay. Whenever I see kind of an acronym explained like this, I think of the episode of SpongeBob of the Krusty Krab training video of POOP. POOP stands for people, order, our patterns. So, it's kind of the same thing, but a really nerdy version. Okay, and so that's all. That's kind of fun and games, but let's actually find out how to actually use Quick. So before we do that, are there any questions on this? Okay, all right. So let's go ahead and see how do we use it. Okay, so just like I mentioned, there's two versions. And so let me go ahead and show you the first version. And so they're not really numbered, but I'll call this version 1. Okay. And so I'm going to show it to you in 1D just because it's a little bit easier to draw. But of course, it extends to 2 dimensions as well. Okay. Okay. And so let's do this actually. Okay, and so if we have phi sub c here, so that's kind of in the middle, okay. And here we have phi sub w, and here we have phi sub e, okay. Right, so those are our 3 cells, and so we have phi sub c, phi sub e, phi sub w, okay. And the edge value that we want to estimate is this one right here. All right, and so you can see obviously for this version, we've added a cell to the left, right? And so if you compare this to our original situation, right? Original situation with phi sub little e in between phi sub c and phi sub e, we've added one to the left here. Okay. Yes, it's a lowercase e because the lowercase e indicates an edge value, right? Right. I use capital letters to denote the self-centered values and the lowercase letters to denote the cell value or the edge values. Okay. And so in this version, what we can say is that phi sub little e is equal to minus 1/8 phi sub w plus 3/4 phi sub c plus 3/8 phi sub big E. And so when do we use this version? We use this version when the velocity is coming from left to right. Okay. In other words, our convection velocity would look something like that. Okay. And so remember, for upwinding schemes, you always want to place more weight on the upstream entities. Okay. And so since our velocity is coming from the left, then it makes sense that we put our additional cell on the left side. Okay. All right. So that's version 1. Version 2, of course, we're going to do the opposite. So let me go ahead and draw a line again. Okay. Okay, and so in this one, I'm going to put the cell over to, I'm going to put the extra cell on the right. Okay, so I'm going to shift things over a bit. And so, you can see here, for this one right here, this is going to be phi sub c. Okay. This is going to be phi sub e. And just like before, we want to estimate phi sub little e. Okay. And phi sub little e is always going to be between phi sub c and phi sub big E. Right? So phi sub little e is right here, okay? And if we add a cell to the right, I'll call this phi sub 2e. Okay. And so, of course, this is going to be the situation when the velocity goes from right to left. So this is going to be in this direction. Okay. All right, and so in this version right here, we have phi sub little e is equal to 3/8 phi sub c plus 3/4 phi sub big E minus 1/8 phi sub 2e. Okay. And so those are the 2 versions that we have for this quick scheme. Okay. All right, I want you to notice something. And so if you look at the actual coefficient values in this quick scheme, you'll notice that they're actually the same, right? And so we have a -1/8, we have a 3/4, and we have a 3/8. Okay. The only difference between the two versions is kind of where they're moved around. Okay? And so, you know, if you look at these versions, you know, in version 1 right here, we put the extra cell on the left, right? And the extra cell always gets the coefficient of -1/8. Okay. Whoa. Okay. And so you can see that the same is down here as well. Okay. And so the 2E1, that's our extra cell, so that gets the coefficient of -1/8. Okay. The cell that's next to the extra cell, that one gets a coefficient of 3/4. Okay. Okay. And so in version 1, you know, because we put that extra cell on the left, then the one that's next to it is phi sub c, right? And so phi sub c there gets a 3/4. And for version 2, you know, in that case, phi sub e is the one that's next to the extra cell. And so that one gets the 3/4. Okay. And then the last remaining one, that gets 3/8. Okay. And so the 3/8 coefficient is for the cell that's furthest away from the extra one. Okay. All right. So I know it could be confusing with the two versions, but you know, just know that there's a lot of similarities. It's just all according to where you put the extra cell. Okay. Okay. Any questions on this before we do an example? Okay. All right. And so I have another example. I don't think we'll actually finish it today. Oh, question. So can we just say that it's a percentage of the weight? Yeah, that's a good way to put it. Yeah. And so you have kind of a fixed amount of weight that you're assigning to the different cells. It's just how you distribute that and what percentage you put on certain cells that determines which version that you use. Yeah. Mm-hmm. Okay. All right. So let's go ahead and do an example. And in fact, it's going to be the exact same example. Because I want to show you that, you know, it's the same, you know, whether you use finite difference or finite volumes. Okay? And so our example here is going to have 10 partial phi partial x plus 75 partial phi partial y is equal to 3 partial squared phi partial x squared plus partial squared phi partial y squared. Okay. And we're going to use the same domain and boundary conditions as we used before. So our domain looks like this. And so we have phi is equal to 25. Phi is equal to 25. Phi is equal to 50. Phi is equal to 50. Okay. And so we want to implement, and so we want to solve this with finite volumes. But, you know, for the convection term, we're going to use the quick scheme. Okay. Okay. And so, you know, we're gonna proceed with this problem just like as we do for normal convection, diffusion, and finite volumes. And so we're going to focus on the 4 integrals, okay? But now, you know, we're gonna have different branching paths, okay? And so not only do we have to check to see if we're on a boundary, but we have to check and see what direction the velocity is going as well, okay? And so we're going to have different versions of each of the four integrals depending on which direction the velocity is going. Okay. And actually, you know, this code is actually quite a mess, and so we have to actually check for three different things. Okay. Okay. And so for each integral, we have to check for these things. So each of these things are going to be an if statement, basically. Okay. And so first of all, we have to check if our cell edge is on a boundary. Okay. Remember, that's what we did before. And so that was the example we did on Monday, on the beginning of class on Monday this week, right? And so if our cell edge is on a boundary, then of course we have to apply a boundary condition, right? Because that's what we're going to need to do for that. Okay. Okay, and so if our cell's not on a boundary, then we have to check which direction the velocity is going to go. Okay. And so depending on which direction the velocity is going, that's going to make us use, you know, quick scheme 1 or quick scheme 2. Okay. Okay. But there's actually one more thing that we have to check, right? And so and so we have the same issue here that we did with our higher order scheme for finite differences, right? And so in order to apply the quick scheme, you know, there's kind of an implicit assumption that we actually have enough neighbors to actually pull it off. Okay. Because if we have enough neighbors, that's great. But there are going to be situations where you don't have enough neighbors. Okay. And we're going to do the same thing that we did for finite differences. If we don't have enough neighbors, then we default to kind of our usual central difference scheme. Okay. And so we have two options here. So we do, if we have enough, we do quick as we usually do. If not, then we do normal central difference. So it's a lot to take in. And so I think from a programming perspective, you know, the implementing the quick scheme is probably the most kind of complex and kind of convoluted thing that we're going to do. Okay. And so it's going to be if statements within if statements with lots of else's. Okay. And so, you know, we're not going to get a chance to look at the code today, you know, but I want you to keep this in mind. And so, you know, the thing with programming is that, you know, programming, it's kind of an exercise in logic. Okay? And so if you kind of understand the logic that's going into the program, then it makes understanding it a lot better. Okay. And so, you know, I want you to kind of remember this, you know, especially, you know, and we have the midterm Monday. So I guess we'll see this again next Wednesday. And so when we see this again next Wednesday, we look at the code, you know, I want you to remember these three checks, okay? Because each of these checks are basically going to turn into a different if statement, okay? But if you kind of follow this logic kind of logically, right? So first we check if we're on a boundary to see if we have to apply boundary condition. Then we have to check which direction the velocity is going to determine which quick scheme that we have to use. And so, you know, from there, you know, we check to see if we even have enough neighbors to pull it off. Okay. And so it kind of, you know, if you kind of approach it from the perspective of, you know, I have to get an equation out of this, then these three checks kind of make a lot of sense. Okay. Any questions on this? Okay. All right. And so let's see how much time. We have 5 minutes. And so let me do one of the integrals here, and then we'll wrap it up for the week. All right, so let's do the east integral because that's the one that we've been doing a lot. Okay. And so the east integral is given by phi sub e times u minus k partial phi partial x on the east face. Okay. And so of course, this is going to have two different versions. And so we're going to assume here that we're not on a boundary. Okay. And so if we're not on a boundary, we have two versions of this. And so we have u times minus 1/8 v sub w plus 3/4 v sub c plus 3/8 v sub e, okay, minus k v sub e minus v sub c, all divided by delta x, okay? And so you can see here that we've added an extra cell to the left, okay? And so that's the addition of phi sub w, because normally phi sub w is the west neighbor, right? And so if we're evaluating the integral on the east edge, usually phi sub w doesn't even make an appearance here, okay? But the fact that we've added it here means that that's where we're putting our extra cell, okay? And so if we're putting the extra cell on the left or on the west side, that means that our velocity must be coming from the left and going to the right, okay? And so this is used if u is greater than 0. Because if u is greater than 0, that means our velocity is coming from the left. Okay. Okay. And so that's version 1, right? Notice how the diffusion term, I didn't change anything to that, right? And so the diffusion is still the same linear interpolation, linear slope as we had before. All right, and so now we have the version 2. And so version 2 is we have u times 3/8 v sub c plus 3/4 v sub e minus 1/8 minus 1/8 v sub 2e, okay, minus k. Again, the diffusion term is not going to change. Okay. And so here, since we put the extra cell on the right, so that's why we have the 2e there, then this is only if u is less than 0. Okay, so that means the velocity is coming to the right, coming from the right. Okay. Okay.
Is that a phi c?
Yes. You mean the first one here?
Yeah.
Yeah, that's a phi sub c. Yeah. All right, so those are our two quick options, but we have to check to make sure if we have enough neighbors, right? If we don't have enough neighbors, or if there's nothing on that side, then we default to the normal scheme. Okay, and so this I'll write it on the side. So if we don't have neighbors, this is going to be u phi sub e plus phi sub c divided by 2 minus k phi sub e minus phi sub c divided by delta x. Okay, so this is the normal scheme, and so this is executed. We have not enough neighbors. Okay, and so really we have three options here, and so we have quick 1, quick 2. But if we don't have enough neighbors, then we go back to our normal scheme. Okay, and so that's just one integral, and so we have three more to go, right? All right, so any questions on this before we wrap it up for the week? Okay, all right, so that's all we got time for today. And so remember, Monday is our midterm, so please make sure to come to campus. So I'm not going to be on Zoom, so please don't be there. Okay? And so Monday we'll take the midterm. Remember, you can have a cheat sheet, 1 8.5 by 11 sheet of paper, and you can bring your calculator as well. Although you're probably not going to need it. Okay? All right, and so if you have any other questions on the exam or anything, I have office hours tomorrow. If not, we can make an appointment, maybe sometime before the exam, and I'll try my best to accommodate. Okay? So thank you everyone for tuning in today. I hope you guys enjoy the weekend. Best of luck studying, and I'll see you guys next week. Yeah.
What would be the lecture after midterm?
So the lecture after the midterm, we'll do the MATLAB part of this, and then we'll start the lecture notes on unsteady finite volumes.
But this the last lecture will not be on or not interesting.
No.
Oh,
Yeah, so the midterm is only gonna be testing you up to diffusion in front of it. So we stopped diffusion actually a while. So basically after, you're only responsible for homework 4, homework 5.
but the last lecture will be on the homework. So will not be on the test.
Yes, yeah. So we have one more homework after this, and this stuff is gonna be on.
Okay, thank you.
We'll have a final, right?
No,
Just
just the project.
midterm, same like midterm one.
Yep, same format. So yeah, cheat sheet, calculator, in person, so exact same stuff. Yep. Oh yeah, hang on. Let me answer this question. All right, thanks, Pedro. Any other questions from Zoom people? Yeah.
Can you move to the,
Wait a second.
can you move to the left? I think you wrote something, right?
Wait, what? Yeah.
Is there something left to it?
Oh yeah. Sure.
Oh,
Yeah. Mhm. Thanks, Chris. Yep. All right, Zoom people, anything else before I sign off? Okay, all right, so I'm gonna go ahead and sign off. So best of luck studying, everyone, and I'll see you all on Monday.